Okay, so what we would like to do after we have looked a little bit at explicit solution for the wave equation last time, where we have seen that the wave equation or the solution of the wave equation behaves differently than the heat equation in the sense that the solution only depends on a portion of the data, and this information is only transported with finite speed of propagation, basically given by the constant in front, or square root of the constant in front of the Laplacian. Everything which is different for the heat equation, we would now like to see what about a general existence result. And we prove existence for the wave equation, or for a boundary value problem for the wave equation, also by approximation, of course, but differently as we did it for the heat equation, namely we use a Galerkin method. So we do not discretize in time as we did it for the heat equation, getting a sequence of elliptic boundary value problems forming piecewise constants or piecewise linear functions in time and correspondingly in space. Out of that, now we keep the time as it is, but we discretize in space. So the equation again is in some sense a general equation. The important thing is only that we have here the second time derivative. And here we allow for a general elliptic operator, which can, of course, be the minus the Laplacian, but also, for example, also an operator not being of second order. For example, it could be Laplacian square, the B Laplacian, which will then come up if we look at a vibrating plate, not a vibrating membrane. And I will explain a little bit so again, we can think of our example, of course. Our example, of course, would be L is minus the Laplacian, and our corresponding spaces is V is being the H10 of omega, meaning that we are looking at a problem with homogeneous Dirichlet conditions. And then we have this pivot space L2 of omega. But this is only an example, and a general situation which should be allowed and which we can handle in one step, so to speak, is Gelfand triple, that we have a Gelfand triple without compactness. So a Gelfand triple of a space V, H, and the dual V prime without needing compactness. That means the following. H is in Hilbert space. V is reflexive and separable. This separable is very important in the following. Of course, it would not be separable. We would not have a basis to approximate it with a then finally countable set. That's basically what it says, this condition. And the norms are correspondingly denoted with the indices, and then we have the embeddings. V going to H. This embedding is supposed to be, of course, continuous and dense, but we don't need compactness, as we would need it, for example, in the parabolic case. And then correspondingly, we have the continuous embedding in the dual space. So these spaces could be those, but they could be also in an example of, for example, of Laplacian squared. We would have here something like the H2. And good question, what do we have here? Probably also the L2, but I'm not so 100% sure. Okay, so, and the theorem is now the following. It first deals only with existence, but it will also bring us an energy conservation, which is very typical for the heat equation. And from this energy conservation, it's not only an estimate, we see basically in the same way as for the parabolic equations that there has to be also uniqueness. So we have the above. Of course I should still say what would be the assumptions on the L, the general assumptions on the L. And the L is, so to speak, related to a bilinear form. And this bilinear form is supposed to be coercive on and symmetric. I think we also need symmetric. So we only have really diffusive forces, no advective parts. Coercive and symmetric in V. Meaning, I think that is very clear to you, meaning that this bilinear form induces a norm, the energy norm, which is equivalent to the norm of V. Coercive, symmetric, and continuous. So we have the estimate, so basically what we need up to the symmetry, what we need in the Lax-Milgram theorem. So we have the estimate from below. AUU is greater or equal than some positive constant norm U square. And we have the estimate from above. Modulus of AUV can be estimated by some constant and norm of U times norm of V. And these both together give the equivalency of the induced energy norm. So maybe we can keep this here as a reminder. The energy norm, let's call it A. That is the square root of this quantity is equivalent to the norm given by the V, the Sobolev space norm. So in this sense, it's an abstract situation, but in some sense, it's the most simple, the abstraction of the most simple situation, what we could have, dealing here with the symmetry. And we will need this equivalency of the norms. We will work with that as we did it, say, in the very beginning, dealing with the Dirichlet problem for the Poisson equation. So let me state the theorem. So these assumptions as they are put down, and the following. So the form which is behind the operator and fulfills all this, and the spaces fulfill all these conditions. Then we have initial data. So we need two. As you know, we have U0 giving the displacement, giving the U, and we have a U1 giving the velocity initially, and both are supposed, the U1 is supposed to be in V, and the U0 in V, the U1 is supposed to be in H. It's not as regular. The right-hand side is supposed to be a function, but it's sufficient that it's an L1 function in time with values in H. So that's a regularity assumption on the data. We have a t less or equal to infinity. That means we can not only handle arbitrarily large time interval, we can also handle the whole time horizon up to infinity. It's a difference to say I have a and okay, the reason for that is that everything will be uniform in time. We don't have this exponential increase as we have it typically in the parabolic parabolic situation. So the assertion is then there is a weak solution of the heat equation in this setting on the interval maybe up to infinity with values in V of the heat equation. And now what means weak solution? In the sense, so let me first specify the regularity of the solution. The U is then an L-finity function. That is also the difference here with a parabolic situation. Here we always had L2 in the parabolic situation because we have this possible growth. And here everything will be bounded in time, L infinity in time with values in V. The time derivative, which is the big problem in a general theory of the parabolic equation, is here immediately a function, L infinity 0t h. The initial data is fulfilled in the trace sense. And now we have to write down the equation. And the equation is, so let me first write down the equation. So what we do, we have test functions. These are now test functions in space and time, called phi. Let me first put it down. C1, compact support in the set closed at, the time interval is closed at t, at 0 and open at t, and the spatial dynamics is in V. That means the support is allowed to go into the 0 because we have to deal with the boundary conditions. For with one boundary conditions we dealt already, but then we have a second boundary condition to deal with, but we stay away from the t. So if we do any partial integration in time, as with what we will do, no values in capital T will show up. So what comes out now if we do this? So we have now this integral in time. Here we do this one partial integration in time. So one time derivative is gone away, and it's gone to the test function. Okay, we can write an argument. Doesn't matter too much, but okay. It's gone to the test function. The whole thing here is in the underlying H scalar product. So it's just if you want the L2 scalar product. So that what has happened. We multiplied with the phi, integrated partially in time. Then we have the term A ut phi t that basically comes from the partial integration in space. That's a good point. Maybe that's not. Maybe one should have said here a little bit more. It's here compatible, for example, with the Dirichlet conditions, with the homogeneous Dirichlet conditions. So it sort of requires, in an abstract form, homogeneous boundary conditions. Because now on the right-hand side, one could also change this. But now on the right-hand side, only this term here appears. And if the boundary conditions, for example, also Neumann boundary conditions would be allowed with another V space, but then also homogeneous, because otherwise we would have here an additional term which would have to be integrated in this V, in this F here, which can be done, but here in this notation it's not the case. So, and now what is still missing is the time are the boundary terms which come from the partial integration in time. And as I said, only the 0 comes up, and so the only point which comes up is here the time derivative, the first time derivative at 0. That is the way to bring the second initial condition in, the u1 here, and correspondingly we have here phi of 0. That's it. So that is the weak formulation. So how do we do this? We do Galerkin. We can in an abstract setting. So that Galerkin does not necessarily mean finite elements. We do it very abstractly, namely so what do we know? We know there is a countable set such that every element in this space can be approximated by a linear combination only up to a given accuracy, epsilon, if we, so to speak, raise the amount of terms which we have as high as it's necessary. Of course, we cannot approximate with a finite dimensional space the whole infinite dimensional space. So it's in some sense it's an abstract formulation of the situation what we have in L2 with the orthonormal basis given by sine and cosine, or given by x to the e x something like times of parameter. So what we have here the separable and that this works, so to separable, and that this works abstractly. That is just what is meant by this word separable. So separable tells us we have elements V1 up to whatever from the space V, such that if we take correspondingly, no, sorry, they are not called V, they are called W. That if we take, strange to call it W, no, okay, it doesn't matter. If we now take the spans of the first K, so the corresponding K-dimensional subspaces, the statement is the following. I take a general element V, and then for this general element there is a sequence, there exists a sequence Vk such that Vk is from this finite dimensional space such that this sequence converges to V, of course, in the V norm. So you just think of these things as something like sine and cosine in the concrete setting. Okay, so now maybe you remember how one deals, for example, with parabolic equations in conjunction with time and space discretization, and there's this intermediate step of the semi-discretization where we say we only discretize in space but not in time, so our partial differential equation then becomes a system of ordinary differential equations, and then we have to think of again approximations of this ordinary system of ordinary differential equations to come to sequences of sets of linear equations. And in an abstract way we do this in the same way. So we define our approximate solutions now in the following way. We are looking for functions uk being functions on this interval, but only, so to speak, with a tuple as the image, and not with a full element in this infinite dimensional space V. So we don't have a V here, we have a VK here. So we have here only a k-dimensional space, we only have a tuple here. Okay, and that means, in general, of course, we can write now this function as a linear combination of the basis functions with coefficients, and the coefficients are now the vk to the top, depending on t. So this is an implicit definition of this unknown function, coefficient function, which is equivalent to find times the basis function wk. And this k now goes, small k goes from 1 to capital K. So this is capital K, and this is also capital K. So that is as semi-discrete approximation. So looking for the UK is the same thing as looking for these k many time-dependent functions here. So in some sense, these are the unknowns, if you want, what we have to determine. So, and what is now the equation? We just require the. So now the point now is we all the regularity questions, which are so hard with does this derivative exist and so on, they are more or less gone now. So what we have here is just ordinary functions on an interval with a tuple image here. It's not more than this. So we can also make requirements on the second derivative. Of course, then a solution with the second derivative will come out. And the requirements for this should be basically that we would have to have the equation. So, but not the equation, of course, fully, because that would mean infinitely requirements from an infinite dimensional space. We can only pose requirements from a finite dimensional space. That means we now test here only with elements from Vk, as in finite elements. And this again is equivalent with testing with basis functions. So we test here with a WL. And correspondingly here in the bilinear form, we also test with a WL. And then we have the right-hand side. And this is for all L from 1 to k. So we pose k requirements, we pose k equations for the k unknown time-dependent functions here. Okay, so actually what we have written down here is now a system of ordinary differential equations, second order ordinary differential equations with which are linear. That means we can then, basically, we can rely on something like the Picard-Lindelöf theorem, which tells us this system has a unique solution on every time interval where we would like to have it. Because the linearity, the linearity independent of t, the fact that here the continuity of this form is independent of t, we don't have here a comma t in the whole thing. That would be, of course, also possible. And here in the continuity, maybe then the continuity constant being dependent on t, that would change the situation. But here everything is uniform in t. And therefore, we have uniform Lipschitz continuity. And therefore, we have unique and global existence. Yeah, and how does this ODE system, this system of ODEs of second order looks like? I guess you know this. What do we get here? So we plug in here this representation, and then we get so to speak, linear combinations here with this for the second derivatives of the vk. Here something with the vk appear, and the coefficients, they come up by having here a wk and a wl in the H scalar product. So a matrix pops up which has the entries mkl being defined as wk-wl. So this is nothing but the mass matrix. In infinite elements, one would call this the mass matrix. And correspondingly here the matrix which pops up here, and this we call A, is in the bilinear form, also the bilinear form evaluated at good, okay. I keep to stick to the notation here. I would write it slightly different, but anyway, it doesn't matter. It's in my notation, this would be the transpose of the stiffness matrix, but this really doesn't play a role here because we have assumed symmetry. Okay. This is then the stiffness matrix. So in this notation, we get, in this notation now, we get the following system. Okay, we could also write it in matrix notation, but let's write it out. We get the following system. We have here the mkl times the second derivative, time derivative of the unknown coefficient functions plus, and now there comes the linear combination with the stiffness matrix. Here the stiffness matrix times the vk and this is equals then the right hand side given by ft with the test function wl. So this is now a system of second order. Of course, if you say, but Picard-Lindelöf only holds true for system of first order, then of course then you rewrite this system by introducing the first derivatives as further unknowns. The important thing is the linear dependence here and the independency from T of this matrix here, giving the uniform Lipschitz continuity in the V, so to speak, of the right-hand side. If you bring this to the other side, this is just independent of the solution to the right-hand side of the ODE system. So Picard-Lindelöf, there's one very slight technical problem here, namely we have only assumed that the f is an L1 function. So we have only an L1 function on this side. So either one has a formulation which allows for that, which is possible, or if one requires that this has to be a continuous function, then one has first to do a regularization step, substituting or approximating this by a continuous function and then going through this approximation step. But the basic thing is Picard-Lindelöf tells us that we have a unique solution in 0t. And t can be infinity, so as large as we want. Okay, so that is our initial, our approximate solution. Of course, now we would like to go to the limit here, and for that we need a priori estimates. So the next step is a priori estimates. Okay, so a priori estimates we get by proper testing. In principle, this is here even, so the typical thing, well, what can we do? What have we learned? So the most important thing is to test for the solution itself. And maybe another thing what one can do or try in this time-dependent problems is to test with the time derivative of the solution if it exists as a function, if it's allowed as a test function. Here it's even more simple because we will not. How do we come to the solution itself? We, so to speak, take all these things here and multiply with the coefficient functions and then sum up, and so we get this back. So it's not that we plug something into the, it's basically the same, into a weak solution, but we just start with this formulation and try to get here the same things in this procedure, what I said. So what we get here, so basically by, let me call it in parentheses, by testing with UK, we get the following situation, and that also means, because then the time integration comes, so to speak, in the end. So first we multiply, then we sum up, and then we integrate in time. We can choose the time interval as we would like. We are not required to integrate in time over the full time interval. So we take any time t1 bigger than 0 or smaller than capital T, to be more precise, and we can get the following. We have the time integral on this interval, and here we have the second derivative of the UK, and okay, I have to correct myself. That is not what we want here. We want not to test with the UK, we want to test with the time derivative of the UK. So we do exactly the same thing what I said, but we don't have the function here in this multiplication and adding procedure, but we have the time derivative. So we get here the first time derivative of the solution, and correspondingly we get the same thing here in the bilinear form. So we have here the UK of t, and here we have the time derivative of the UK of t. And also in the right hand side we also then have the time derivative. So why is this of advantage to look at this form? This is now basically, so what we would like to have, we would like to have things, we would like to have estimates of the UK or some norms of the UK which are independent of the k, which do not explode if the k becomes larger and larger. And why we did this here, and that is here, what is this here? This is nothing but, and we have no problems with this function, because these are just quite ordinary second order continuous functions with second order time derivatives and a finite number of values here coming out of this ODE. So we don't have to worry about these terms and know how to deal with them. And so this is nothing but then the time derivative of then the time derivative of, and let me first write it in this form, the time derivative of UK with itself, or let me write it directly in the norm. So this is here the H norm, so the H scalar product, the H norm squared. So we might look at this term as the kinetic energy term here in the whole thing. And in the same sense, also this term, of course, can be written in the same way. Here we have the bilinear form given by the scalar product of the H. Here we have the bilinear form given by the A, but that's the only property what we use in this consideration. Exactly for the same reason, this is 1/2 the time derivative UK in the A norm squared. Just another bilinear form. So we have two derivatives here. So we can, so to speak, write out the integrals over these derivatives, fundamental theorem. So we have, on the one hand side, the time derivative of the UK, in the H norm squared. Then we have 1/2, doesn't matter how to write it. Maybe I write it directly in this norm. You have the UK in the A norm squared. So I have, if you want, kinetic energy plus potential energy here, once evaluated at T1 and once evaluated at 0 from this integral over the derivatives. So I have a difference of the energies. You have the energy at the time T1 compared with the energy at the time 0. And the only thing what can change this energy is this right-hand side term. Which, okay, in the special case that there is no right-hand side, we have a homogeneous equation, then we see directly conservation of energy. This total energy in this definition stays the same, is constant in time. There's nothing dissipated, as in the parabolic equation. Nothing goes away. It's just everything is conserved. So now we are here in the more general situation with the right-hand side, but that is now basically technique. So what we have to do is we have to estimate this right-hand side in such a way that the solution-dependent part, which is still in, becomes so small that we can absorb it here in this part. So maybe I shorten it a little bit. So the right-hand side, the typical estimate of the right-hand side, of course, first of all is I get the modulus in, and then I have some estimate here of the H-scalar product. Of course, I then take the Cauchy-Schwarz inequality, and I have something like here the H norm of the F times the H norm of the UK. And now, as we did it several times, I can separate this product in sums of squares where I can shift the importance. So I can give this part a small coefficient with the aim to absorb this part here. To do this correctly, let's first see how this is with the time integral. Here we now just estimate this first. So what we could do, of course, we could have L2 in time, but of course we can also shift a little bit between. So the extreme would be, seems unwise now at the moment, do we have a very heavy norm here? The most heaviest norm in time would be the L infinity norm. And this is then just, here we only need the L1 norm then. That's a trivial estimate by taking the supremum out, so to speak. So we have here from the F the L1 norm in time, and therefore this is also sufficient for the assumption on the data. And here we get for the time derivative an L infinity in time H norm. Okay, so the next step is, of course, to separate this with an something like an epsilon, this thing squared, and something like constant over epsilon with this thing squared. And now, why is this enough? Because now, as we have here an estimate for every instance of time, every t1, we also have it for the supremum in time. And then we can, if this epsilon, say, is 1/4, we can absorb it here in this term. So maybe it's not necessary to write down all the details. So what we get is, we get an estimate for the supremum in time for all our, yeah, we can, at the moment nothing is continuous, so it's not so, it doesn't matter whether I integrate the boundary values or not, it just doesn't mean anything. So I get an estimate here of the time derivative of u h, and on the other, basically, and here I have something like the plus, okay. Now this term I also have, so I also have here also uniform in time. That's also different with the parabolic situation. Uniform in time, not a derivative, but only the function itself. But now in the A norm, so to speak, in the Sobolev space norm, in the V norm, and the estimate is by constant times in this constant exactly the data terms appear. Maybe I write it like that, c times data. And the data is this one, and the data are these corresponding terms here for t equal to 0. So here we get the u0 in the V norm, and here we get the u1 in the H norm. So this is the a priori estimate. So to write it in words, we have a uniform estimate. We have a uniform estimate in which spaces in so we have UK uniformly estimate in uniformly, so L infinity in time with values in V. So this is the second part here. And we have even a time derivative. So we have a W1 function. The time derivative is also uniformly bounded. So W1 infinity with values in H. So what can we conclude? So we can conclude, of course, we can be less ambitious and say, okay, L2 is also nice here and here. Then we are back in the realm of reflexive spaces. And if we look only at the estimate in L2 and W12, so in H1 in time, which is, of course, in particular true, then we get a corresponding weak convergence. So first thing is, we have a weak convergence. We have a UK weakly to some U in L2 0t V and also in the time derivative, so in H1 0t H. That in the end, we always have the same limit. That is this argument that all these notions of weak convergence in particular have the consequence of distributional convergence. And in the distribution sense, if we have distributional convergence, we have also convergence in the distributional sense of any derivative. And so these things becomes comparable. And so the limit of the derivative function must be the derivative, at least in the distributional sense, of the other limit. So written out, this would mean UK converges weakly to U, and time derivative of UK converges weakly to time derivative of U. So this always this referring to the distributional convergence brings, so to speak, the things together. But we have here more. We not only have L2, we have here L infinity. The drawback of L infinity and here W1 infinity is that they are not reflexive spaces. So we cannot refer to weak convergence, but only to weak star convergence. I hope you remember what this is. That is, if you are in a not reflexive, you are in a dual space, but in a non-reflexive situation, and you have, so to speak, a weak formulation of a topology, but the topology is not defined by V double prime, not by the full dual space, but only by the embedded space V, which is a difference in the non-reflexive situation. So what we have in addition is we have weak star convergence, and now, but all the limits are the same by this argument in this original space L infinity. So, okay. So what does that mean? Now we have to go to the limit. We have to go to the limit, and if we now look here at the formulation of the weak notion of solutions, we have to allow for certain test functions which are time dependent with values in V. So what we can do at the moment, what we have here basically is if you look here at this formulation, what we have here is a sort of a testing, not with a function in V, but so to speak with a constant in V. Of course, we can now blow up this constant by bringing in a time-dependent function. So this will be the first step which we do. So we have test functions of special form. We start with test functions of special form. And see how we can go through the limit with this form, and then how we can go on to come to the general test function. The test function should be of the following form. They should be, so to speak, general in time, but in space they should be constant in space, should be only have one value, namely just one of the space's elements here. So if we take the psi correspondingly smooth, so what should it be? It should be a C1 function with compact support, where the support can go into the 0 but not into the t. And here that's just the reals. We have a special test function of this type, which is here. So to speak, the test function's constant with specific constant values. Now this test function we can handle. So the W we have handled already. Now we multiply. So this statement, this ODE statement is so to speak pointwise in time. So we multiply this with the psi, and now we integrate in time, and then again we can partially integrate in time. So that's the procedure. And so we get, so we take the equation. So I would here multiply with a psi, so I get here this test function phi. And here correspondingly, all is linear, goes through. The psi can go into the bilinear form. So now I integrate in time. To do the same thing also with the right-hand side. So now I can do partial integration in the first part. Yeah, why I'm not? Sorry. Ich bin gerade in der Vorlesung. Meine Tochter macht gerade Abitur. Okay, obwohl, Mathe ist ja vorbei, ist eigentlich nichts mehr los jetzt. Sogar Deutsch ist schon geschrieben. Okay, so where was I? Why don't we stick to this formulation? Of course, this formulation would be much better, but we cannot go to the limit. We don't know anything about the second derivatives here, so we are satisfied with a weaker formulation, and then we can hopefully go to the limit. So we have by partial integration in time. We now get, so to speak, our weak formulation. Maybe I write it. Is it necessary? Okay, I start with the first term. The first term is just now the time derivative where one of this integral, but one of the time derivative now has moved over to the test function. And the rest is as before. And now by this integration in time, we get this additional u1 phi 0 term here with a second initial condition in the whole thing. Now question is, can we now go to the limit? And now we see there's no problem with that, because what do we have? We have here at this level we can even do it with the first formulation. We have a weak convergence here of the time derivative. This is fixed, so to speak, fixed test function. So this term converges, this term with the a, which I have not written down, which has not changed. That's the same thing because of this statement here, and the right-hand side is independent of the solution. So we know this holds true also for u, for the limit. So this was for the special test function. Now we have to have these general test function. General now means with general values in V. And this we do in two steps. So these are, so to speak, from the point of view of the test functions, these are all continuous functionals here. If we can show that this holds true for a dense set in this large set, in this large space of test functions, we are done. So we have to approximate now the general test functions by functions which are nearly of this type. So if we can do this type, of course we can also do, so if we can do one value in space, we can also do finitely many values in space. So that would mean that all these integrals, which are the spatial integrals, which are hidden here and which are hidden here, has to be broken up in this finitely many sets, and then we do exactly the same thing of each of these finite subsets and include the whole thing together. Why is this enough? Let me show you that this is enough. So now we have a general test function. That is, we have now a function, call it phi tilde, which is C1 in time, with these requirements concerning compactness and with general values in V. So now we look at the time derivative of the whole thing. Call this eta tilde. This is now at least an L2 function. So this L2 function now And this we can do. This is just the notion of basically one part of the notion of Lebesgue integration. This integrable function we can approximate in L2 by a sequence of functions which only has a finitely many values in space, what is called a simple function in integration theory. We have reminded this looking at the Buchner integral. So what do we get is, we get an approximation phi tilde epsilon, and phi tilde epsilon is of the same type, which is piecewise constant. Let's say the error is up to epsilon. Now we have finitely many values in V, but still not in Vk. But those finitely many values in V, each of it, can be again approximated to any given accuracy with values in Vk. So that's the next approximation step. So now we approximate with the second approximation step this V epsilon tilde by n V epsilon tilde k, which is piecewise constant with values in Vk, with correspondingly large k depending on the epsilon requirement here. So now we are back, as I said, basically to the situation here where we had one value from Vk, or the basics value, and now we can first, as I indicated, go here from one value to finitely many Vk values, and this reasoning now showed, maybe I clean a blackboard. This reasoning now showed that we are done in the sense that we have found an arbitrary good approximation, a dense set, for which we have verified already the equation. So we have verified it for all test functions. So let me finalize this. Oops. Was ist da los? So, okay. So now what we do is we take the test function let's call it phi tilde epsilon k. So we took both approximation steps. So we started with the derivatives. We now integrate again in time. This gives us the smoothness. So we have done with a minus here. We don't have to worry about that aspect. So we can have the derivative as we would like, plug this in, and then epsilon to 0 gives then the general, let's call it a general weak formulation for the general test function. So that's it with the existence proof. So let's see what can be added as remarks. Maybe now, after I've done this proof quite in detail, I will skip some of the further proofs. So again, let's compare what the situation is. If we have here the wave equation, and we compare it, let's say, with the heat equation. So what is the consequence of this, having here 2 time derivatives and here 1 time derivative? It seems so less in between, but it's quite some consequences. Here we have an infinity solution. We have a uniformly bounded solution with values in V. We have a uniformly bounded time derivative. No problem about existence as a functions with values in H. And because of this, now if we use the corresponding embedding theorem, we have the second time derivative, an affinity function, and now here the thing with the dual space comes up 1 level shifted, so to speak. In the heat equation, we only have L2, 0T, V, and we have L infinity, so we got a pointwise estimate, but not in the V norm, not in the Sobolev space norm, but only in the H norm, in the underlying L2 norm. And here, because everything is 1 order shifted, we get, so to speak, this problem, is it a function or not, already at the level of this first time derivative. So at a second glance, this is quite not so extremely astonishing. So now what about continuity in time? So that we can really speak about the initial data also in a classical sense. And that is what is stated in the next theorem. And it says basically the assumptions which we have. We need a little bit more on the f. The f is supposed to be an L2 function 0th. It's not only an L1 function, that's the only difference. And then that's the statement. There's always to be under, but this holds true in general. If we now say one of those integrable functions is a continuous function, it always means, of course, in the equivalence class is a continuous function. So we can change the function on a set of measure 0, getting a continuous representative of the class. That's a general interpretation independent of the specific situation. So in this sense, we now know this u is a continuous function on 0t with values in v, and the time derivative is a continuous function with values in h. And we have the energy equation with which we have argued, namely the energy in the sense of kinetic energy, so time derivative in the h norm squared plus potential energy, so u in the a norm squared times 1/2. This is, if I now see how this changes between instances in times t1 and t2, such a change is only due to a term of the type source term times time derivative of the solution. So if there's no source term, this quantity stays constant in time. Okay, the proof is quite similar. We have to first smooth again and then see how this transfers and so on and so on. And then finally, final corollary for the heat equation. Then we try to go a step further. has two aspects. The one is the one point is uniqueness. We have not looked at uniqueness, but maybe we can handle uniqueness. We can even handle uniqueness at this level. So what about uniqueness? So let's assume that we have two solutions, U1 and U2. The difference, we have a linear problem, difference is also a solution, but for the source terms. So I think we should be able to add even uniqueness here. Don't see any reason not to do this. That is, the solution is unique. And we see this from this energy equation. Why? If we now apply this energy equation to the difference, the right-hand side is gone because the source term is now 0 here. That is, we have here the difference, we have here the difference, and that means these things are constant. So they are the same as for the initial data. Yeah, okay, there's one technical point which I see actually this argument should be postponed. Now I see why we not really know that this continuity is really going up to 0. That is the argument which is still missing. So let's assume we know that. So that these quantities are the same as at u equal to 0. At u equal to 0, this initial data is 0 and this initial data is 0. So all these quantities are 0. These are just norms here. So the u being the difference is 0. But okay, for technical point, it's too early to formulate it here. So we do it in the next corollary, which gives a slight variation, namely the following. Maybe I make it very short. I write it in this form. Now you see the minor but important difference here. And correspondingly for the time derivative, the same thing. So the continuity of these quantities, they go up to the initial point. The initial point has not such a initial point of time does not have this character as in the parabolic equation, that there is something very crude data and then out of the sudden everything changes. The initial point is not very specific for a hyperbolic equation, and therefore it can be included here, and because of this, by the argument I've already given, the solution U is unique. Only to indicate how we could prove this here. What we know already is that we have the continuity at an interior point. So we have to make the 0, and if you want also the capital T to be an interior point. So we have to prolongate the solution beyond of T, which is no problem, because we said if the data allow, they can exist on every interval of time. So we can just think the interval a little bit larger, T plus epsilon, and then this T is an interior point, and we get the continuity at this point. How do we do it with the 0? That would mean we have to go into the past, which in the parabolic equation we cannot. In the elliptic, in the heat equation, we can go to the past. There's no problem, because in the heat, do we have it somewhere? Maybe I indicate it very briefly. Make T equals to 0 interior by going in the past. Can we go into the past? Let's have a look. So I write down again our equation in the most simple situation. That's this one. If we now go, let's say, to this time transformation, what happens? What happens? with the equation? What happens? Nothing. Because we have two time derivatives. Compare the heat equation. If we do the same thing, a lot of things happens. Now we get a minus in, or if you want, we get a plus in here. So we have a totally new equation. And that is the major difference. So because of this, we can also take our data and go backwards in time with our initial result. So we get also for the wave, there's no difference going backward and forward. For the dissipative propagation of a heat equation, there's an enormous difference. So just by this, yeah, I think that's enough. Then we can add, so to speak, some interval in negative time. T becomes an interior point. Then we have this. Okay. I think that should be enough for the heat equation. We still have a little bit of time. So let us start with our next subject. And our next subject, this will cover us a little bit more than just the next 20 minutes, but nevertheless we can start with it. That's the Navier-Stokes equation. So we have seen already some existence theory for the stationary Stokes equation, and one might now think, okay, now we have some idea how to handle linear time-dependent equations. So maybe with these techniques we have seen we could do also something for the time-dependent Stokes equation. But the Navier-Stokes equation is again something different because it has this nonlinear term in it. So where is it? Oops. We can start with a little bit of technical preparation for that. So the procedure, of course, will be again the same thing as before. We would like to define approximate solutions, show that those approximate solutions exist in some weak sense, find a priori estimates, would like to go to the limit, and so on. The same procedure as before. Now first of all, for the Navier-Stokes equation, which is an equation which, so to speak, mixes the elliptic and the parabolic and the hyperbolic aspects. And then maybe also, if time permits, we look at the pure hyperbolic system of the Euler equations. But let's first start with the Navier-Stokes in the most simple form. So we have the incompressible Navier-Stokes. So of course, one can also look at the compressible Navier-Stokes, which in some sense is easier. Don't know whether it's easier or not so easy. But we will rely here very much on the incompressible Navier-Stokes, on the incompressibility condition. So let me write down the equation, how it should look like, time dependent. So we have our vector field, which is here denoted by V. So this is a field with 2 or 3 components, the velocity field. And you see basically everything is normed to 1. I would say too much is normed to 1, but I keep it in this formulation here. I think it's a little bit too much set to 1, but okay, for the existence proof it does not matter. So we have our, so to speak, is it okay? I think so, because we look at it source free, then it's okay. So we have the velocity field, then we have the convective transport term, which is now our nonlinear term here. So the vector field drives the vector field. Then we have the gradient of the pressure, the inviscid part of the stress tensor, and the viscous part is here fully reduced to the vector-valued Laplacian, so the viscosity is scaled to 1 in this formulation here. That is one equation, and then of course we have the divergence-free conditions. And then the boundary conditions are supposed to be, so this is in Qt to be understood, and the boundary conditions are the so to speak, the hardest are the conditions v equal to 0. Velocity field is 0, fully 0 on the boundary, delta omega t. And of course we have initial data. Okay, so of course we would like to basically the same thing as before, finding weak formulations and testing correspondingly. And we've seen already what possibilities we have with Stokes equation. In the Stokes equation we had two approaches. We had one space where we incorporated the incompressibility into the space, and as a consequence here this term in the weak formulation dropped out, and then the rest was quite simple in the Stokes equation. On the other formulation, which was then a mixed formulation, where we kept, which led then to the settle point formulation, where we kept the where we looked at velocity fields without these incompressibility conditions, and then had these two unknowns, the v and the p. So we will first do the first step and see what we get with the testing. Okay. Upsala. Wieso ist das jetzt alles total durcheinander? Okay, let's look a little bit at the convective part, which is new. The first observation is the convective part can be written as a divergence. Why? Let's just write it down. So what does that mean? We have v times gradient applied to v, and from this the jth component. What does that mean? Writing it out, we have an operator which is a sort of a scalar product of the vk, of the partial derivatives of the delta k, k here from 1 to n being the spatial dimension. And this is now applied here to the Vj. Okay. Yeah, but this here, I claim I can write, not this here, okay. What is this here? Let me maybe put it this way. I would like to write it in this form. Derivative of Vk Vj, which is of course not correct in general. Because if I differentiate this out, I get this term, and I get in addition the term where now the derivative sits here. So I get, where the derivative sits here. So I get here the kth derivative of the Vk times the Vj. But now I'm not looking at these terms separately, I'm only looking at the sum. And looking at the sum, I get here the sum of this part here. And what is the sum of this part? What is this? That's the divergence, and we are looking for divergence-free situations, so the sum is 0. So that means under the divergence freeness, we can write this here as this derivative, so we can really write it as a divergence of something. So we have a field where we look at the partial derivatives of the components of the case derivatives, and the field is Vk, Vj, and then we sum up. So if you want, we have here the divergence of, you might remember this is just a tensor product of these two vectors. It's just the derivative of V in tensorial with V. So that's another way to write this term. And this might be of advantage if we then go to the limit. Let's say we do have a limit consideration. We have a limit consideration in the following sense. Assume that we know that we have a sequence Vm which converges strongly to some V in L2 and which is divergence free. So we have no assumption whatsoever on the convergence of derivatives. Okay, now let's have a look here. So we know, because of this strong convergence, we know that all these products here converge strongly in L1. L2 functions times L2 function gives an L1 function. That means we have distributional convergence of the derivatives. So what we have then, because we have identified this term here as a derivative, we have distributional convergence then of Vm, what otherwise is not so easy to see, because this is, as we just have seen, the divergence of this tensorial product. And let's say distributional, the same thing here, because here we have L1 convergence, and this again is this quantity. So we get, without any assumptions on the on the convergence of the derivative, we get a strong L2 convergence through this term. This is then just this thing here. So that's the first remark. The second remark is testing with V. That's the first thing we would like to do. So we test all the equations with V that we did with the Stokes problem, and then we knew what happened with all those terms, a part of the new term. So maybe the new term now brings in problems. So let's have a look at the new term. What is the new term? The new term is I've got V times a gradient applied to V. So, and this has to be tested with V. So now let's write out this whole thing, component by component, that we see what is happening. Maybe this can be done a little bit more elegant, but okay, we just write down everything what we have. So we have the V case. Here there's this scalar product, and then we have from here, we have, this from here, we have the Vk, and we have the kth derivative, and this we apply to the Vj, and this we multiply with the Vj. So, okay, so what does that mean? let me see. This is now, maybe I first write it down, then we can see that it's correct. This is, I claim, the V times the gradient applied now to 1/2 V squared. So why? Because that means we first differentiate this thing here, then we get the scalar product with a V, and then we get the application of the operator here. So here we can now do partial integration, and is this correct? Okay, let me first write it down. Divergence of V. Yeah, we just do the divergence to this part, and then we have times this part. So, okay. But this here is 0. That is, in the testing of V, the nonlinear part gives no further contribution. So what we could do for the Stokes equation is the same thing as we can do for the Navier-Stokes equation. The problems will come up if we test now with a time derivative. Testing with a time derivative otherwise that would mean the Navier-Stokes equation is as simple as the Stokes equation, what is not the case. Testing with a time derivative to go further in regularity, this now really brings in additional things. So the basic theory we can, so to speak, repeat from the Stokes equation, and then we get stuck. So this is also reflects this general picture. It's clear that in any dimension we have a weak solution of the Navier-Stokes equation, but if we ask ourselves, is there more regularity globally in time, then this question is even open. So, okay. As I said, testing with the time derivative of V now brings in additional terms. So now this term is this term V divergence, divergence applied to V and tested now with the time derivative of V. So this term is in general not equal to 0. Final remarks, and then we can think this will then we have enough. Let's have a look at this form here. This form BU VW. So this triple form, this trilinear form, let's say. This trilinear form which we get if we take this convective part and give all the quantities different names. So the U is the driving field. Then we have applied it to some other field V, and then we test it with a field W. So this is a trilinear form. And let's see which spaces can we allow for these. So what we would like to have is, we would like to have something like Y, which is H1 0 because of our boundary condition, omega vector valued. So this would be one possibility. So we take the u and the v from this space, and but then it's not so clear what for the w is allowed. The only thing what's allowed then for the w is so what comes then out is something like a buv applied to the w is being this thing here, and the b is then something like from y cross y to y prime. So that would be a standard situation. But now the question is, can we vary a little bit? Can we shift a little bit the regularity? So what is possible? And that is the following observation. So the only thing to give the whole thing a sense is that we have to look at the sum, which the term which is behind this form here. And that's a term which has a component of the u, which has a component of the gradient v. So we have here a derivative, uk, and the corresponding derivative of the vj, and then a wj. So I have three functions. So we asked ourselves, when is this product of three functions an L1 function? We can do this in two steps with the Hölder inequality. Or what comes out is then, of course, that we have to have LP, LQ, LR spaces, if you want, and 1 over P plus 1 over Q plus 1 over R must be 1. So this is sort of an extension of this duality of the LP spaces. So what could we choose? Yeah, we could choose, for example, that is one thing, and on the other thing, we need what we have here the H1 function. So we need here, let's say an LP, we need here an LQ, and here's something an LR. And we have to have 1 over P, as I said, plus 1 over Q plus 1 over R equals to 1. And on the other hand, we have to have these. So we have to have that H1 has a continuous embedding, for example, in LP. So now we have to remember the embedding theorems. And the embedding theorems basically say that depending on the embedding theorem says that we have a continuous embedding if we go a little bit down in the weak order of derivative which we do here in any case. We go down from 1 to 0. But then there's a little bit room. So what is, of course, an obvious embedding is H1 to L2. That is nothing to prove for that. But there's a little bit room in this embedding theorem in the sense that we can also allow for a larger P here. And what comes out here, what is allowed here is and that depends, how much is allowed depends on the dimension. The larger the dimension, the smaller the gap becomes. That's the reason why in one dimension an H1 function is still continuous, but in higher dimension it is not. So as long as the space dimension is less or equal than 4, which is okay, P equal 4 is allowed. So we have an embedding here to L4. So that means, what does that mean? We can choose here to make this thing well defined. So here and here we have our H1 function. So here we take P equals to Q equals 4. So we have 1 over 4, 1 over 4. And so here we have a 1/2 left. So we can choose R. I think this should be okay. Where is it? Where is it set? Wait a second. Not for the Q. The Q is critical because there's a derivative. For the R, we take this. So here H1, here H1. So of course this is not an H1, but it's an L2. So Q is equal L2. So this makes sense. So this makes sense. So this operator is in general well defined on H1. This is what we have seen here. Also, we have this construction with the three functions to be multiplied. Okay, so next time we will try to use these technical things and to come to some weak existence result, or in the direction of a weak existence result of the Navier-Stokes. Okay.